All right, so I know a couple of you guys had issues with the friction lab. How many of you got that finished? Because I am going to give you guys, I can give you a little time to wrap it up. Right, so like Meg, you can get those done. I'll give you like 5 or 10 minutes. I can help you. There's a certain part that didn't make sense. I was feeling it was supposed to be pretty straightforward, right? It goes step by step, uses that simulator. Did the simulator work okay? Did you guys get my video about part 2? I sent you all an email, and I explained for part 2, you have to do the static friction. The static friction is the instructions they're not always as clear what you exactly have to do. You basically have to apply a force very slowly, and the moment the object started to move, you remember what that force was. That was the goal for part 2 for static friction. All right. So what I'm going to do, I need you guys to put your phones and stuff away. I'm going to give you guys a little bit more time to finish up loose ends on the friction lab, and then I want you to turn those in. The lab is really important. I told you guys labs are a big part of this AP class. So the grade weight of labs is much higher than just a homework lab. Right? So I want you all to turn something in. Virtual students, same thing. If you filled this out electronically, submit that file. If you did it, printed it out and wrote it all in, just upload pictures of your lab. But I really want you all to turn one in so I don't have to give you a half credit on a lab. And again, I'll go walk around and see if you have any last minute questions like finishing this up. Did it work okay?
Yeah, no.
And then down here, you want to do a linear curve fit, and it'll spit out the statistics.
Okay.
And then you got your slope and intercept. You didn't figure it out? Mm-hmm. Was I going to move off of static? Oh, no, I mentioned it in like to do it slowly. Yeah. They should all be higher. For the same object, you should have a higher static than Yep. Sweet. Did everybody's graphical analysis work okay? Again, if you use your graphing calculator, that's fine. You just needed to make a graph, a plot of your data points, right? It told you plot this on the x, this on the y. Because this relationship is a big part of friction. You guys were exploring it. It kind of led you to some conclusions that you might not grasp fully. But what I wanted you to do is to explore, figure it out on your own. And if it doesn't quite make sense, that's when I'm going to come in and I'm going to explain it fully and hopefully connect these dots for you. That's why I did it lab first, then material, rather than the other way around. Sierra, did you get it to work? I had gotten a couple of your emails and responded. Did it make sense? Yeah, static.
A little bit.
Did you notice that your static? Yeah, these all should be higher. Yeah, those look good.
Okay.
Yes, your static friction should be higher than for an object than the kinetic. And those all are. Yep, that looks good. You got these figured out?
Yeah, I just didn't understand some of the questions.
Okay.
I'm not sure if I did it right.
That's okay. Again, I'm not going to grade this for right or wrong, because this was more exploring.
Mm-hmm.
It's leading you to some conclusions, but they might not all be there yet, and I'm going to tie them together. So it's okay if you didn't. If this wasn't easy for you, that's fine. That's actually my expectation. Is it's some new stuff.
Okay, so randomly the lab,
Brody's done his.
randomly the lab really today, so I could start it, but I'm not gonna finish it.
So it didn't even work when you got home.
So I don't know why. It's just like, hey, I'm gonna start it.
Click it, see it. Oh, for goodness sake. Because yeah,
I had it open for
we didn't.
the whole thing.
Did you restart your computer since then? Because usually you reboot and reset it up.
Oh yeah, I did that yesterday in Ish.
That's probably why.
Because I was
If you ever have computer problems, do a restart. That's like Tech 101.
Except here's the thing though.
Or IT 101 rather.
Well, I couldn't restart it from here. I actually had to like hold this down. When I hit the restart button, it wouldn't restart.
Why wouldn't it?
It would just when I hit restart and when you hit restart, it says like that. I pressed the restart button, nothing happened. So I just had to.
Did you wait like 30 seconds even? Because sometimes it's trying to shut everything down, and it might be like processing the button.
Well, I
On your
sat there,
power
I
button.
sat there and waited, and then I waited
Yeah,
a
he
little
did
bit.
that.
I waited a little bit, and then I did it a second time. It still didn't do it. So then I just forced it.
Okay. You had some tech issues. What I can do is I can let you turn in like this evening on maybe be able to finish it.
Well, problem is I tried
Yeah.
this and right after that I was on vacation. So for then, so I'll be like 5:30.
Okay. If you can do it tonight, that's great. Otherwise, get it to me like tomorrow.
Okay,
And then I can still give you full credit for your computers.
Oh, you're doing
Is that fair?
Really?
Yeah. Yeah, and then you can just send me pictures, right? I just need to see that you did it.
But what exactly do I need to do?
The whole thing.
Yes, but what do I have? Well, what do I need to?
We'll follow the
do?
instructions, right? Part 1. Click all these. You're going to click all those. Each match, you're going to push it until it's moving quick and then let it go. The red arrow will be magnetic. Solve for gravity, that's easy. And complete the table, right? So one box, you're going to, the mass is 50, you can calculate gravity. Normal force, you know, is equal. You hold this. You're going to start, keep going. See how it's starting to move? Now let it go. That red arrow, that's your friction force. That's what you want to record. Well, then you're going to switch and do all this and record that. Same process.
So then I put.
Yeah, you take the box out, put the name in.
Oh, I think the box. And I take it back.
Yep. Same process. Push it. Yep. Apply your force. Push it. Get it going. Get it going. Get it going.
Oh.
The 150. Now let it go. 150 is what you recorded for the name.
Oh, for the friction.
Yep. Again, that's what the instructions say.
Okay, but and then
This one, this should be static. That was my email. I emailed you how to do that.
yeah.
When you do the static, you're gonna look. It's gonna go like this. You're gonna push him. He's not moving. Go slow. Not moving. Not moving. Not moving. Right there. The 150. Oh wait. 200. You see how it went from 200 and then started moving? That 200 is what you write down for this. This should be static. This is a pipe. That shouldn't say static. Or kinetic. It should say you're static. These should be the equal, right? Gravity pulls it down, normal force supports it. That's in the y direction. These should all be equal. This is that left and right. So that would say basically x-axis is normal force. Yeah, those are your x numbers. And then these, right? Friction force is your y number. So x is y, x is y, x is y. And then you plot those. Yeah, so y equals 0.22 or 0.244 plus x plus yours minus 0.47. Ready?
Because for some reason this would I get to say you can say this one.
Okay. So you have tech issues. Can you finish this tonight?
You could try.
Okay. If you have it into me by tomorrow noon, just email me pictures of everything done. I can give you credit. Okay, I won't be super available. I have professional development all day tomorrow, so I'm not gonna be like, I won't be super ready. I'll try.
Try and ask questions.
Yeah. Yeah, I mean this one, these instructions. You did this, but this one, that was my email. My email, I have you a video on how to do this process. And then the rest is just Q&A. So you should be able to do it. If you don't know it all, give your best crack at it.
Okay.
Right? Just complete it. That's the important thing.
So you're not going to do any of the DuckTales stuff tomorrow?
No, I don't really know what Ducktail is.
Oh, you got
It's like
Car show, right?
Cars, yeah, you'll love old cars.
I love cars, so I'm actually very intrigued. The only problem is...
Tonight at the high school, they're having like a car show thing.
Yeah.
The whole park.
Yeah.
Oh, really?
Yeah, that's the fundraiser as far as the band sells tenderloins and stuff.
Oh, tenderloins. I love tenderloins.
You should go.
Oh.
It's really fun.
It is. It's very
I'll just come to the one
I feel
tonight.
like you
You're
don't
not
order
going to
at least once. I think since it's your first dovetail in Indiana, you kind of have to go at least.
Yeah, I'll have to ask my wife. Because one, I was a little nervous. We get groceries on our weekends. Well, I've heard that tons of people flood this area, and so I'm nervous about like, 'cause Walmart will be a frickin' zoo.
That's
Right?
why we don't go to school tomorrow because the traffic
Well,
gets so
true,
bad.
but I think like real bad
This event takes up 95% of the gas city's income.
for the year.
Yeah.
Yeah?
It really
That's
does.
probably true.
That's accurate, I
That
feel like.
that actually doesn't surprise me.
Just wait.
That,
It's
maybe
like-
I'll
It's like our own holiday.
It really is.
I'll have to ask my wife. Yes. The point is, it's weird,
It's so weird to see the
right? I'm pushing slowly. 180.
And it's like, it looks so empty.
124.
Grass.
And then it switched back to the net to 124, and then it changes to static. Do you get what I'm saying? You push it slowly, it'll get big, and then as soon as it starts to move, your force will drop. You want the force right before it drops. So you have to go slow to pay attention. And that's why that part's tricky. That's why I sent that video.
Yeah, I'm confused on like what, like, so, I know like
This you just can't work. This is just literally empty. This time's not going
okay, but
Easy.
then,
Yes, no, that's.
You know normal force, right? Gravity force pushes down like 30 force.
Yeah, 9.8.
Yeah, that's the force gravity. What supports that principle? The normal force.
Yeah.
So the normal force will always be equal.
Well, it's equal to, but then,
Because it's not moving in the y direction. They balance.
what am I supposed to be putting like for the numbers we were saying, so like, when it starts.
So let it go. And stop. Let go. Let go. No.
Oh.
Yeah, there. You see that? Friction force 94. That's it.
Oh, that's okay.
There's the instructions on the prior page.
Yeah,
Tells you
I was reading that, but I wasn't quite sure where.
push the object till it's moving. Then the friction force by the red arrow would be your kinetic friction.
But I know that where say kinetic that was also supposed to be stacked.
Part 2, my email said. Part 2, that's static. This was a typo.
Oh, okay, so it's only here.
Yes. Yes. Yes.
This,
Say that again.
Did you get it?
It's a load. Yeah.
for,
I got it to load, yeah.
this would be like 125.
Maybe 94.
Zero. Measure right there.
Yes, it's moving.
So.
Says equate force.
Oh, that's the net force. So if you say, if it's moving, don't you have kinetic friction that acts on it?
Will explain the physics of no, no.
Exactly.
Hey, Mr. Schwartz told me you have these now? Yes. Yes, they're in this part. Are you just returning this to me? Or? Okay. I'll put that in there. All right, here you go. Thank you very much.
No problem. It's not.
Oh no. Oh. Never mind.
Oh.
Okay, that makes sense. Now it's nice. We figured it out. Yeah, we got it.
That's what you
So,
said.
that one is saying
I just didn't start it.
you're pulling it, right? This force is against it. And it's causing motion. Well,
Now we do
the friction that exists, we calculated that. So the net force is pull 15 to the right, right? Oh yeah. So it's just slow. So the force would be negative, whatever. Yeah, it's really, yeah. Sorry, I agree that's a weird
You
question.
got that for the kids. It's me, Bob, me, the girl.
It's a symbol, it's called the U thing. The slope is that coefficient. So it says the slope is this value. So you literally say this value is my slope. It's telling you that variable is the slope of this graph. Just write down the slope. Yeah, so that's your slope. Yep. Your book is follows
Where's it?
Like what? What's that?
You haven't put, you don't know.
No. Never heard of it.
No, he's not a loser.
Oh. Easy.
Calm down.
Okay. So what I need you guys to do is turn these in, right? I need to get going with the rest of the material that we got today. So I need you to turn these in. If you guys, here, I can take them if you're finished. Otherwise, you can give them to me later today. But I need to get going. Yeah, your name's on it. Thank you. You guys got yours?
I could finish it in I have to ish. Yeah, ish.
I really need it now. I might give you guys till the end of class. Yeah, just at the end of class, turn those in. But I need to get going. So what I need you guys to do, get out your student workbook. I have one of these that I want to do related to friction. So student workbook. Did that turn off? Dang it. We're doing 2F. It's just one of these on friction.
Say 2F.
Is that not connecting? Is that getting clear? Anyway, whatever. Okay, so 2F, I want us to do this together. Looking at the direction of friction. Now, this should be easy, because you guys have done this friction lab to start to get a taste for friction. We got this bulldozer pushing a big block. They're speeding up. If it says they're speeding up, what do we know is true about this system?
Acceleration.
There's acceleration. Good. That means there's some net force acting. So the first thing, what forces are acting on the bulldozer? What's our number one force we want to always go with? Gravity. Good. What resists gravity?
Normal.
Right? It's sitting on the ground. Gravity's trying to push it down. The normal force counteracts it so that it doesn't actually move in the y direction. So they balance. What's allowing the bulldozer to move forward? Yeah, the ground. It's that friction. So moving forward, this is, we can do F friction, say ground. We can do it that way. Is there any other forces acting on the bulldozer? The block. Good. Right? You cut around the bulldozer. Everything you're cutting through, you got to put. Well, that block is pressing on the bulldozer's, right, the loader on the front. That creates a force, but it pushes back on it. We're going to do a little force. F block. Right? We should be, we'll get very good at free body diagrams. They're very important for this class. Now, we're going to do F equals ma. We're going to do capital M for the bulldozer and some acceleration, and we'll specify it's in the x direction. What forces are causing this acceleration? Is gravity contributing to this acceleration? Yes or no? Guys, yes or no?
No.
No. It's in a completely different direction. Normal force is in the y direction. That has no bearing on the x direction. I have these two forces. So if I know it's speeding up going this way, right, the direction that it's moving, this has to be bigger. That's why I drew it this way. Free body diagrams. Your vectors that you draw need to have a magnitude, meaning how big it is, and it also needs a direction. So I'm going to put, we'll say F friction ground minus F block. Friction pushes this way, the block opposes it, while the resultant, the net force, is what actually causes acceleration in the x direction. Now we can do the same process, but look at the cube. Well, same thing. My cube. Force of gravity, a balanced normal force. It's an object on the ground. Gravity is trying to pull it to the center of the earth, so we have a gravitational force. And the normal force on the ground is what's supporting it and keeping it stationary in the y direction. These add up to 0, so there's no acceleration to this object in the y direction. Now, obviously, this bulldozer is pushing our block, right? So we definitely have force bulldozer, right? I guess I'll call it that. I'll do force B. The bulldozer is pushing this block to the right. The same way that the block pushes back on the bulldozer. Or wait, excuse me. Yeah. Pushes on the bulldozer. So really, I should have drawn this really big, and I need to draw these equal to each other. The force that the block pushes on the bulldozer is equal and opposite Newton's third law. I drew this a little smaller. That looks about the same-ish. Right? If I push on the block pushes back on me. Well, what else is acting on the cube that I'm trying to push? Friction. Right? Friction is opposing the motion. So I got this little friction force. Now if I sum my forces in the x direction, little m times ax, right? F equals ma. The mass of this object is the mass of the cube, little m. Well, what forces are there acting in the x direction? Yeah, I got this big friction force, or excuse me, the bulldozer pushing minus this little friction force. The leftover, the net force, that's what causes the acceleration. Now, we're going to look at the entire bulldozer block system. We're going to treat them as a combined object. We don't care about this anymore. We don't care how much the bulldozer pushes on the block and the block pushes back. They're a part of the same system. I don't care what they do to each other. I want to know what's happening to that system. So again, I want to cut around my system. Well, what forces are actually acting on my bulldozer block? Gravity. How should I draw my gravity compared to the gravity of the block or the gravity of the bulldozer?
It's going to be very, very much.
It's going to be big. I really am just going to add these up. This is going to be really long. Because now the force of gravity, it's the bulldozer and the block. So I add these two forces. My normal force, equal and opposite. Now, what forces act on the bulldozer block? Friction. Right? Which direction is the friction going? Do we think it's moving to the left or to the right? This is probably very confusing to you guys.
Yeah.
Well, first of all, in the x direction, is there anything else acting besides friction? No.
So it has to be right.
Yeah, Ethan's saying it has to be to the right. Well, he knows that because we're moving to the right. We're accelerating. There has to be a net force to the right.
Because it's working against it.
Not quite, because the tracks are pushing this way, right? The tracks are trying to spin backwards, but friction resists. That's what lets you go forward, right? These forces cancel out. These are internal forces now. My bulldozer pushing on the block, and the block pushing back. Well, if I'm looking at both objects, I don't care what they do to each other. I want to know what happens to them as a whole. So this, I don't care about. So I will have a little, John, you're right. I'm sorry. I think I misunderstood your question. There will be a little bit of friction. You're correct. There is a little friction that resists the motion. That's always true. So John, I apologize. I didn't understand what you were saying. That's my bad. There is friction that opposes the motion. That comes from the block. The block is sliding and friction is trying to oppose it. However, the tracks are using friction, exactly. Then I got this big F ground, right? Force of friction on the ground. Do you see this? The friction from the tracks is pushing everything forward. Now there is a little friction of the block sliding that slows it down.
But it gets canceled out, and then there's
Yeah.
more left.
The net force, right? Do this a little too big. So I got, what's the mass of my system?
N plus N.
Yeah.
Plus little n.
I have the same acceleration. The bulldozer block is moving the same as either the bulldozer or the block. That should make sense. However, my system is now both objects. So I need to make sure I show that in my Newton's second law. The mass of my system is this piece plus that piece. Well, what forces act on it? I got F friction ground minus F friction of the block. Now this one's going to win. This is a lot bigger. The net force here is causing that motion. Do we follow that? What questions do we have? What doesn't make sense about this? And please, if you don't get it, you're hurting yourself by not asking, can you explain this again? I want questions. I want to know when you get something. I especially want to know when you don't get something. I don't like to move on unless everyone's understanding it, because then I end up wasting your guys' time by going to a new topic when we didn't even get the first thing. Does this make sense? Our free body diagrams is a very important skill. AP is very particular about it. Right? We kept the direction of our forces always going outward from the object. We could have drawn them pointing in and touching, right, being applied on, but we would have to keep that consistent. The system is important. What objects you're considering. This was only the bulldozer. Imagine cutting around the bulldozer and any forces you're cutting through, you need to show that. Then we looked at just the cube, and then we looked at the total system. To look at the total motion. This is like the important piece, because this describes the motion of our system of the bulldozer block. Newton's second law makes sense? F equals ma. How fast are they accelerating? Well, we didn't know. We just represented it by A. What's the mass of our system? Easy. Our system's these two objects. I just add the masses together. That's what the mass of my moving system is. I look at what forces act on that system in the direction of acceleration, add them up, whatever I get is what's causing my motion. All right? So then, if you look down at part C, we did part B together. We already did these. It's going to ask us to do the math. So I'm going to leave this equation up down here. It wants us to use that. The mass of the bulldozer, big M, is 1,000 kilograms. Little m, the rock, is 500 kilograms. Friction force on bulldozer, which is FF ground, is 5,000 newtons. And the friction on the cube is 2,000, F little f. And I want to, sorry, here, I'm going to do this. Again, read the question. AP will like to trick you by asking difficult questions. So that means you need to just slow down and read the question. This is what I want. I want to tell them the acceleration. Well, in your head, you're thinking, well, I got an equation with the acceleration. Do I know all the other variables? Well, write it out. My full equation that I wrote from the previous step. Force of friction from the ground minus force of little friction is total mass times acceleration. Well, this is right here. So I got 5,000 newtons. What's the friction on the block? What did it tell me? 2,000. Does everyone know how I got that? These variables were given in the equation. I just had to put them in the right spot. The friction on the bulldozer was the ground friction at 5,000. Friction on the cube was 2,000. So then what's my net force?
3,000.
3,000. I just do my math. If it's a positive value, what direction is it going?
Forward.
Yeah, it's in this direction. That is equal to, what's the mass of my bulldozer? 1,000. 1,000 plus 500 times acceleration. Right? This is just algebra. Once I do this, the hard work's over. You are only doing algebra after this step. This is physics. This is just math. This is easy. This is plug and chug. This is easy. Easy. Then I literally, what's my algebra? Well, shoot. I got to divide by 1,500 on both sides. So, I'm running out of screen time, whatever. What's 3,000 divided by 1,500? Huh? I was going to say, Brody, come on. Brain burp. 2 meters per second squared. Right? Now, I know this because if I use newtons in kilograms, if I use my base SI units, my answer will be the base SI unit, meters per second squared. Now you can also realize, what are the simple units of newtons? You guys remember that? What is a newton? Yes. Kilogram meter per second squared. Well, if I took this divided by 1,500 kilograms, is get rid of my kilograms, right? So I can tell it that way too. That's your answer. Free body diagram, sum of the forces. Use F equals MA, plug and chug, figure out the unknown. Physics. We get that? Basically, that process we're going to do over and over and over. Now it's going to get more complicated, but this process is exactly the same. What forces are acting on which objects? What do I know? Use Newton's laws. Get those equations. Plug in what you know, solve for what you don't. Alright? Now, what I want to do is I want to actually formally talk about friction. So again, feel free to take notes on this. I would recommend it. Otherwise, make sure, again, I'm going to try and connect the dots from the friction lab and talking about friction. I'm going to formally, explain it to you. Even though you should know it, it's just, we started learning it through a lab rather than me just telling you what it is. Right? Not all good physics is just learning material. Sometimes it's doing it for yourself. So when we have friction, when you pull on something, Right? You try to drag something along the ground. Friction opposes it. We write friction as F sub F. Capital F for a force, and then a lowercase subscript, little f, to indicate this is a friction force. Friction opposes motion. It does the opposite of what the motion is trying to do. If I'm pulling on this pallet, I'm trying to pull it this way. Friction will oppose me and act in the opposite direction. That's what friction does. Friction is sliding between two surfaces. It doesn't want to slide, so it resists. It always opposes motion. You see this schematic up here? Do you know that objects are never actually smooth? Do you know that? Right? Everything has a certain roughness to it. This is a zoom in of like a microscopic level. If you keep zooming in on where the wood and the concrete touch each other, it's actually very rough. Right? You see all the little indentations, all the grains of the wood. If you look at concrete up close, it's very rough. It's like got holes in it, pits, peaks and valleys. This is why friction is such a big deal. All these roughnesses and peaks and valleys, it's like Velcro. They get stuck on each other, and it makes it hard to move something. That's what's happening. What happens if I have this pallet and I put a bunch of sandbags on there? Am I going to have to pull harder, the same, or less to get it to move? Harder. Do you know why that is? Yes. But if I get it pulling at a constant speed, say there's no acceleration. Say I get my pallet, I pull it and it's sliding at a constant speed. There's no net force. I'm just pulling with a certain force and it's sliding. Well, if I'm able to pull a pallet with sandbags at a constant force, is my force to keep it steadily moving going to be bigger, smaller, or the same as without them? It's going to be a lot bigger, right? I would have to pull way harder to keep this sliding on the ground. What? It is. But what specific reason? Something changed when I put more mass on there. The friction. This will make it very difficult. Because if it's at constant motion, it doesn't matter how much that force is. If this was on an imaginary ice surface, I'd just need to pull it and get it moving, and then I would actually pull with zero force. Because it's in constant motion. It's not accelerated. But that never happens in reality. Friction goes way through the roof. Right? My gravity force gets bigger because I have more mass. That means the normal force has to get bigger as well. If I take this object onto ice, is it going to be easier for me to pull it or harder? Easier. Right?
Except you also don't have any friction anymore.
What's that?
I said except you also don't have any friction anymore.
Oh, that's true. That's a great point. Let's assume you got studs in your shoes so you can grip the ice. Do you see the differences? Wood on concrete and wood on ice? I don't know, I can't really zoom that in anymore. The wood is the same, but do you see that the ice is much less pitted? There's less roughness and peaks and valleys? That should make sense. These surfaces should slide easier than these. This looks like Velcro. They're going to get stuck on each other all the time. On ice, it doesn't. Here's a better picture. You see it when you're pulling? All these bumps are hitting each other, getting caught on each other, rubbing against each other. Did you also notice these two words? Those should look familiar from your lab. The reason you had to look at these two is there are two types of friction. Now the names explain themselves. Static friction is the friction force when something's stationary. Right? When I try to tug on something and it doesn't move, what prevents me from pulling it is that static force, or static friction. It's when things are stuck together. Right? Yeah. Ethan was in his chair. Thank you. That's actually a really good example. So Ethan was on his chair, and he was trying to get himself to move. He's pushing on the table, but he's not going anywhere. I'm pushing, but nothing happens. Well, how can I apply a force and not cause motion? That violates Newton's second law.
Friction, you're applying enough force.
The static friction. The friction on the bottom of the chair resists my motion. I'm pushing this way, so the table pushes me back, but friction resists me. There's another type of force on the bottom. That's friction when something's in motion. So if I'm pushing, I'm moving the table. If I'm pushing and then I'm in motion, friction's still resisting me. Right? There are two types of force. If you have friction resisting motion but nothing's happening, that's because you're static. Static should make sense. Kinetic is when you're actually in motion. This is really important to get. Static friction is what you need to overcome to initiate movement. Kinetic friction is the force you have to overcome to maintain that movement. Once you get an object going, friction's still going to resist you, but it's different. And you overcome kinetic friction to keep it moving. You see this? They're pulling, nothing's happening. And then it starts to move. You guys see this? They're pulling. The static friction increases, they're equal and opposite, and then it moves. Did you notice the friction vector? Watch this vector. Gets bigger and bigger and bigger and bigger. Do you see it switch?
That's very cool.
It instantly dropped a little bit as soon as motion happened. Did you guys notice that on your friction lab? My video was specific because I needed you to apply that force slowly and see that you apply a ton of force, and then as soon as it starts moving, that force changes. That's because you switch from static to kinetic friction. Here's an example. Static friction of 1 Newton, nothing happens. Static friction of 3 Newtons, nothing's happening yet. Now how about kinetic friction? I keep pulling. Then, did you see the needle? I pull. It's up to 3, then to 4, and then it slips and goes back to 3. It's harder to get something to start moving than it is to keep it moving. It's a big thing I want you guys to be aware of for static versus kinetic friction. Now we have double the mass. I'm pulling, it's nothing. Then it starts to move and it drops. Right? I had to pull with 8 newtons in order to get it to move. But then once it was moving, I could pull with 6 and I could keep it moving. I also want to point out, do you see how this is less than or equal to? If something's static, I could pull with 1/10 of a newton. The static friction would directly balance me at 1/10 of a newton the other way. I could pull at 1 newton. It would counteract me at 1. I could pull at 4 newtons. It would counteract me at 4. This happens all the way up till 8 at its limit. The moment you pass this limit, it starts to move, and you don't have static anymore, you have kinetic friction. Does that make sense? I don't think there's anything else. This is another thing we're going to talk about. The friction force proportional to the normal force. So it's true, the more massive an object is, the more gravity acts on it, and therefore the more normal force supports it. Well, the more normal force there is, the greater the friction. This is also showing you, different surfaces have different frictions. Same thing, wood on concrete has high friction. Wood on ice, not so much. Glass on ice has crazy low friction. Those surfaces slide across each other very easily. So you have very low friction. Now this should make sense. Rubber on granite. That's why people like KitchenAid mixers, they got a rubber bottom, right? A rubber seal or rubber feet. They have insane friction. You don't want your mixer made out of glass on the bottom, because it's just going to slip and slide on your countertop.
Makes it better.
They put rubber feet because there's high friction between those two materials. It would take an insane force to get that mixer to start sliding. This is how engineers use physics to make good products. Right? So what engineering is, using physics and science to make things or to benefit people. You guys remember this little guy? Does anybody know what this symbol is? It's a Greek letter. The coefficient of friction. It's mu. M-U. Or if you're into Pokemon, Mew. They're spelled differently, but same word. I always wanted to catch Mew. I played Pokemon when I was a kid. I'd heard that you like randomly find it. It's like one of the rarest in the game, and I never found it. I was super upset. This Mew, Ethan said, hey, it's a coefficient. You guys remember the coefficient you determined? All this coefficient does is it describes the friction between two surfaces. This is our friction equation. This particularly is static friction. The friction of an object depends on the coefficient, which is basically describing the interaction between two surfaces. Which of these comparisons, like glass on ice or rubber on granite, has a higher coefficient of friction? Rubber on granite, right? You have way higher friction values. Well, if your objects are the same, this number has to change. High coefficient of friction means high friction forces between two objects. Do you see how kinetic is an equal sign? Once you have an object in motion, there is a set kinetic friction force. The same, no matter how fast or slow you pull it, if it's in motion, it will respond with this much friction force. Static friction will be anything you want. It'll completely balance you out until it hits its limit, and then it switches to kinetic. This is a very, very important graph I want you to understand. This is describing an object on a table, say. This is how much force I pull on it, and this is the friction force. Do you see how anytime I pull on the force, or on the book or whatever, the friction balances me out? It's linear. Whatever I pull, that's how much friction it is. And whatever I pull, that's how much friction it is. However, what happens right here? Do you know what this is describing? Yeah, right? If I'm pulling on my chair, I'm pulling a little more. You see how it started to move? It gets to this limit, and then it gives out, and then I'm in kinetic friction. It's easier to keep an object in motion than it is to get it to move. This is slip. This is when the object actually starts moving, and my friction force is no longer static, it's kinetic. So I want you to realize friction or static friction force will balance out your pull until it reaches its limit, and then it'll slip and go to kinetic, and then kinetic friction will be the same no matter how fast, how slow, whatever. It'll resist a certain amount. Notice, these are different coefficients. The static friction of, say, rubber on granite isn't always the same as sliding rubber and granite. Now, we look these up. This is a massive list of two materials and their coefficient of friction. Engineering Toolbox is a great site. I use this all the time in my engineering classes. They have all kinds of equations, data. Huh? No, we haven't done anything quite as advanced or that you need data like this. But, you see all these coefficients? 0.2. Holy smokes. 0.04. A waxed ski and snow have a coefficient of friction of 0.04.
You zoom in on that.
That makes sense. Do you understand why we use waxed skis to go skiing? Do you understand why we wouldn't use wood? Let's see. Oh, there's not another snow comparison. Dang it. There's wet snow, yeah. Anyway, makes sense, right? I don't want a lot of friction. I want to go fast. I don't want something slowing me down.
What about a water ski?
Oh, I don't know. You could probably look it up. You can look up the coefficient of friction depends on the two surfaces rubbing. Now, it could be the same surface, but, metal on metal has a certain coefficient. Plastic on plastic, whatever it is, you need to look up the coefficient. This is also important. This should make sense. If my friction equation is friction equals coefficient of friction times normal force, my static friction is large, and then it gives out to kinetic. So the coefficient of static friction is always going to be larger. Always true. This is a really tricky one. You have a tire rolling on the ground. Where's the friction happening? Right here, isn't it? Friction's happening right at this contact point. Are those two surfaces sliding across each other? No, they are not. When your car is driving, it's not sliding. You have static force or static friction. Every time you're rolling, the contact point is pushing against the ground and moving your car forward. It doesn't slip. That's what's called a burnout. Burnout, you don't go very fast. You just sit there and spin. Yeah. Why is it dangerous to drive in the winter than it is in the summer? You might slide. Why might you slide? It's the same tire.
Because there's ice on the road with less friction.
Exactly. Rubber and ice has a very low friction. We need friction to move a car. If that's low friction, I don't have a lot of friction force to get me going. That's why you slide in the winter. In the summer, rubber and asphalt, It's a huge friction coefficient. You got grip for days. You can go typically however fast you want. It's also why, what if you get stuck on ice? What do they put on the road to give you grip? Salt or sand. Now salt acts not only to give you grip, but also to melt the ice so you can get to the pavement and get higher friction. But sand, all it's doing is making rubber on sand more grippy. Gives you more friction, lets you drive. It changes the interaction. What about skidding? Kinetic or static friction? Kinetic. You have two surfaces that are rubbing in motion. Did you know this is why ABS brakes exist? ABS brakes, if you don't have ABS, you hit the brakes and start to slide, you're just going to keep skidding.
Until you hit something.
Kinetic friction is worse than static. You can't do much. You just slide. So what they did is they said, we want static friction all the time. As soon as my car senses sliding, it's going to let go of the brakes and pump them on again. It wants static friction. If I lock the brakes up, I'm just sliding. Well, if I lock them up and let go and lock them again, I get static friction. It goes from static to kinetic back and forth. Yep, and that's why ABS exists. You don't want this. You can't stop in time. Okay. I think that's the last that I want to do. I did not get as far as I'd like. I had one more lab that I wanted you guys to do. Oh. I always run out of time in this class.
It ends up in a rant sometimes.
We're going to have to push that back to Monday. Yes, Tuesday, thank you.
Wait, do we get Monday off?
You get tomorrow.
Oh,
Tomorrow.
never mind. We don't have this class on Monday. I got confused.
Oh, these are confused with that.
Well, no, 'cause we have stuff to do.
Okay. What I'm going to do,
Oh. You're
Mason's here.
yeah.
okay, so you guys, I want to, I'm probably going to have to do the lab Monday. Tuesday, sorry. I'm trying to think and talk. Yes. The other, I don't want to introduce this yet. I'm going to make this a video and have you guys watch that for the weekend before we come back on Monday. Excuse me, Tuesday. Dang it! Oh my gosh. I am very ready for the weekend, if you cannot tell.
Ready for nuts yet?
I am toast. Oh my gosh. Huh?
You need it now.
I do.
You need the tender one.
And I have like 15 kids coming in ISH to make up tests. It's going to be another zoo. What I'm going to do is I'm going to try and make this, I think tonight, I'm going to present the next set of notes called Hooke's Law. Hooke's Law is about springs. We're going to look at spring force. I'm going to make a video where I go through this on my computer and talk to you. That is what I'm going to assign to you as homework so that when you come back on Tuesday, I'm getting it, you guys are going to have background info on Hooke's Law. So the lab should be really easy. Now, I wanted you to do the lab, explore a new material, struggle with it, and then I'll connect the dots for you. But I'm going to switch it this time. So you guys understand, your homework will be to watch the video that I made. I'll make it, and I think I'll post it to Classroom, get it to you guys. And I just need you to watch that, ideally take notes, try to understand Hooke's law and spring forces so that when you come back, we can do a lab quickly. It should make a lot more sense. We can connect dots doing the lab rather than the notes, and then we'll carry on with other material. Huh? Yes, Hooke's law is the force or the law that describes spring forces. It's really cool. Aiden? Watch The Office. That'd be nice. The problem is I have like 7 kids retaking a test. 4 of them are doing a quiz. It's going to be a mess. My poor Ish kids, I have to tell them, like, do whatever you want, just be quiet, because I got to let them take their test, without a zoo. So yeah, that's what I'll do. Oh, Friction Labs. If you didn't finish it, I'll accept it. Not late, but you get it to me before you leave, I can give you full points. So everybody, you got yours? Any Friction Labs?
Yeah, good. And the rest of it's just like answering questions.
Aiden, you got yours?
I think I did.
I'm not crying myself to sleep.
Maybe.
Because I know next period I cover something that's discussed. Like, you have to work on it. It's the only thing you ought to work on. I feel like
Maggie,
literally how it is.
Are you going to Ginger?
I don't know.
It's fine.
We're on our last bowl Texas Roadhouse.
I'll give it a nice.
Courtesy Championship.
Friction Labs, you guys have yours?
When are you gonna get? Do you know yet?
Yeah,
That's whatever you're in the mood for.
my boy. That's what I always
Anybody else have a Friction Lab that I can get? Oh, yeah. Oh, you guys have issues.
on this. I'm too picky when it comes to steak. I cannot have a single ounce of fat on it right now. Yeah, so I have to get the filet and chance to be like, oh, John, my
Yeah, I feel like steak's one of those things that you don't want that on.
Yeah. Well, some people like it.
No,
Well, but sometimes if it's cooked right, it's just
Sometimes I
melt in
email
your
them
mouth,
to
but it's
myself.
still
Yeah.
Oh, yeah.
Put it on.
Did you know you can email from your phone?
Yeah,
Yeah.
I know, but I just.
You can type a text to your email and it'll send in.
You can have a text your email?
Uh-huh.
I'll bet. That's what I'm gonna do.
Yeah. You can text to your email directly.
I didn't know that.
You should be able to. If you want to email to your cell phone, you can do it, but you have to do like your phone number at vzw.com or something. You can look up, like, there's email codes for text numbers for certain carriers. So I actually use that to reach out to my virtual students. I send out an email to all student-parent emails and student-parent phone numbers using, that extension. So they get an email text from me. It's really handy.
Probably like 1,000 emails a day.
Can I know?
Feels like what?
Where's the bathroom?
Yes. We get out at 45, don't we? Yeah. Yeah.
Literally,
Yeah.
never lose them.
You're welcome. I'll let you guys hang out the rest of class. I'll let you get on your phones if you wanted to. Hope you guys already are.
I mean, I guess it makes sense. They don't